The concept of a holographic universe is built upon a profound philosophical and scientific idea known as ontological democracy. This perspective suggests that the two-dimensional information encoded on the boundary of the universe and the three-dimensional space we inhabit are equally fundamental elements of reality. They coexist and emerge from one another, with neither being more real or more primitive than the other. The deep implication here is that the three-dimensional reality we perceive from vast galaxies to the stars in the night sky might actually be a manifestation of deeper, fundamental laws encoded on a distant boundary. This is an exploration of our cosmos, and while it may not offer practical changes to your daily life, the story is a long one, best told in the realm of dreams. Before we dive in, remember to like and share. We begin with the fascinating possibility of life beyond carbon. This starts with chemical similarities. In the periodic table, silicon sits directly below carbon. Both are tetravalent elements, meaning they can each form chemical bonds with 4 other atoms, creating the complex frameworks necessary for life systems. In 2016, a team at Caltech led by Francis Arnold successfully synthesized molecules composed entirely of silicon and carbon. Their research demonstrated that organisms like E. coli can produce proteins containing these compounds, proving that silicon-carbon bonds can indeed exist within a biological framework. Consequently, scientists have concluded that silicon-based life is a distinct possibility beyond Earth. To understand if silicon could truly replace carbon, we must define life itself. Scientist Norman Pace suggests that life is the ability of an organism to self-replicate and overcome evolutionary hurdles, such as developing organs for movement. Therefore, the building blocks of an organism must adapt rapidly to new environments. Beyond chemical complexity, life requires specific ecological conditions: oxygen, nitrogen, stable temperatures, and a solvent like water. Many compounds, such as salts, dissolve easily in water, allowing different parts of molecules to recombine and form new bonds. Carbon provides the long, stable framework for these water-based organisms. But can silicon form these necessary connections? The short answer is, not easily. While silicon-based life might exist, an organism entirely made of silicon without any carbon might struggle to support the chemical complexity required for high-level life. We have yet to find such life on Earth, though silicon is a vital secondary component in many terrestrial plants and animals. For instance, our oceans are home to diatoms, mysterious algae with cell walls made of transparent silica. This doesn't make them silicon-based life, but it proves silicon can be a fundamental part of a biological build. For other worlds, research led by Riccardo Gabrieli suggests that the ideal environment for silicon life would require very little oxygen or water, temperatures either above 428 degrees Fahrenheit or below freezing, and atmospheric pressures much higher than Earth's. It would also require solvents like sulfuric acid or methane. Some places in our solar system nearly fit this description. Saturn's moon, Titan, with its lakes of methane and ethane and a nitrogen-rich atmosphere, is a prime candidate. Venus, despite its crushing heat and pressure, possesses yellow sulfuric acid clouds where silicon-based molecules might theoretically form, though the high carbon content there might still favor carbon-dominant chemistry. We must also consider silicon's versatility. While silicon can bond with nitrogen, hydrogen, oxygen, phosphorus, sulfur, and various metals just like carbon, it lacks carbon's extreme adaptability. Silicon fails to form suitable chemical bonds in water and struggles to bond with other elements within the standard temperature range of 0 to 100 degrees Celsius. It tends to react only at extreme temperatures, making the formation of life-sustaining structures difficult. Furthermore, silicon is far less capable of bonding with itself than carbon is. Silicon atoms cannot build the massive, intricate frameworks that carbon can. Consider a diamond, it is pure carbon, showcasing the incredible strength and complexity carbon can achieve. Silicon, however, has a powerful affinity for oxygen. This is why silicon-based life is unlikely on Earth. Silicon almost always exists as silica or sand. If we were to replace the carbon in our bodies with silicon, we wouldn't breathe out carbon dioxide, we would essentially be exhaling sand. Carbon's role extends beyond respiration into the very core of nutrition. Food is our primary energy source, and when we are weary, a good meal is the best remedy. However, the true source of that energy is the carbon compounds within the food, such as glucose. When we cannot eat, our bodies break down stored carbon compounds like starch for fuel. If these bonds were made of silicon, they would be far more unstable and likely unable to support the metabolic needs of a living being. So, while silicon may participate in life processes, a purely silicon-based organism remains highly improbable. Even on carbon planets, worlds formed far from their parent stars with abundant solvents but little water, the birth of life would be a painstakingly slow process because silicon-carbon compounds like silicon carbide are incredibly stable and require immense energy to break down. If silicon-based life did exist, how would we recognize it? Science fiction often imagines living stones, like the creatures in Star Trek. But in reality, silicon life wouldn't necessarily look like a rock. After all, we aren't covered in diamonds, and diatoms are far from stones. Scientists suspect silicon life would be chemically simpler and perhaps less intelligent by our standards, meaning we might never encounter a sentient rock person. Because of their unique molecular signatures, our current detection methods might even miss them entirely. It is difficult for us to imagine life in environments so alien to our own, which is why most space missions focus on life as we know it. While we cannot confirm the existence of silicon life yet, the universe is vast. We cannot rule out the possibility that among billions of galaxies, life isn't always built on a carbon foundation. Imagine standing at the edge of a boundless ocean, the surface shimmering with the reflections of the cosmos. Now, imagine that this entire panorama of stars and galaxies is actually just an image reflected from a distant, hidden shore. This isn't science fiction, it is the perspective of the holographic principle, one of the most compelling theories in modern physics. Just as a single dewdrop on a spiderweb can contain a miniature model of the surrounding world, our universe may be a grand reflection. Its fundamental laws are written on a boundary far above the ground we walk and the void we observe. In other words, the mechanics of our reality may stem from a deeper existence beyond our current reach. At the heart of physics, the quest for the most basic elements of reality, ontological primitives, never stops. For centuries, titans like Isaac Newton viewed space as an absolute, unchanging container, indifferent to the matter within it. But with Einstein's relativity, space became an active participant, capable of stretching and curving. From this evolving view, the radical idea of the holographic principle emerged. It suggests that our three-dimensional perception is a projection from a two-dimensional surface at the edge of space. This boundary, though infinitely far and invisible, contains all the information of our world. Every star, every galaxy, and even gravity itself are emergent phenomena, a bridge between our observed dimensions and the hidden holographic code. Black holes provided the first real clues to this mystery. Stephen Hawking and Jacob Bekenstein discovered that black holes are not just dead ends for matter, but key players in the exchange of cosmic information. They found that a black hole's entropy, a measure of its hidden information, is proportional to its surface area, not its volume. This counterintuitive discovery implies that the information capacity of any region of space is determined by its boundary. This laid the foundation for the idea that all the information in our universe could be encoded on a two-dimensional shell. To bridge the gap between black hole physics and the holographic principle, Juan Maldacena proposed a specific model showing a duality between a type of curved space and a quantum field theory on its boundary. Even though our universe is slightly different in its curvature, this duality provides a window into how dimensions emerge and how the macroscopic structures we see, stars and galaxies, are the collective behavior of fundamental patterns on the holographic boundary. This leads us back to ontological democracy, the idea that the two-dimensional code and the three-dimensional world are equally real. In this framework, even gravity is reimagined. Instead of a direct force, gravity might be an entropic force arising from changes in information on the boundary, much like how temperature emerges from the movement of atoms. This theory, championed by Eric Verland, suggests that gravity is simply the universe's tendency toward a state of maximum entropy. Furthermore, the very fabric of spacetime might be woven by quantum entanglement. When particles are entangled, they share a connection that creates the illusion of continuous space. If we were to break these entanglements, the space between particles might simply vanish, challenging our entire concept of distance. The ultimate goal remains a universal holographic model, a single framework that can describe both the massive cosmos and the tiny quantum world. Achieving this would revolutionize our understanding of the origin of the universe and the nature of black holes. If reality is indeed holographic, then our perceptions and our very existence are more deeply connected to the cosmos than we ever dared to imagine. The journey is full of unknowns, but the prospect of uncovering the deepest secrets of the universe keeps us moving forward, searching for the model that will redefine our place in the stars. Imagine if the universe were composed of tiny fragments, so small they are invisible to the naked eye. Imagine that these fragments are whispering to us that what we know as gravity is merely the beginning of the story. For centuries, gravity has remained a profound puzzle. We once believed we had solved it, thinking of it as a fundamental force, an invisible thread binding the entire cosmos together. But modern physics suggests that the truth is far more bizarre. Have you ever wondered why gravity can shape entire galaxies yet remain completely invisible to our senses? Some modern scientists now believe that gravity might not be fundamental at all. Instead, it could be an emergent phenomenon, arising from the entanglement of particles and the very fabric of space-time itself. If this is true, then everything we thought we knew about gravity might be wrong. New experiments are already being designed to test this theory, and if they succeed, they will fundamentally rewrite our understanding of the rules of reality. Let's take a closer look at how this story unfolds. At first glance, gravity seems simple enough. It is the force that makes objects fall, keeps us firmly planted on Earth, and governs the movements of celestial bodies. However, upon closer inspection, gravity reveals itself as one of the most mysterious forces in the universe. Among the four fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, and gravity stands alone. It is the weakest of the four, yet it operates over vast distances, holding galaxies together and using its influence to sculpt the architecture of the entire cosmos. The uniqueness of gravity lies in the fact that it only ever acts as an attraction. While electromagnetism can both attract and repel depending on the charge, gravity only pulls things together, whether it's a tiny speck of dust or a massive galaxy. This universal attraction creates a profound order, influencing everything from the formation of planets to the largest structures in the universe. At the most basic level, we understand gravity through Newton's law of universal gravitation, which tells us that every object exerts a pull on every other object, proportional to their masses and inversely proportional to the square of the distance between them. But while useful, this doesn't explain the underlying mechanism. Why does gravity act in this specific way, and how does it reach across the void of space where other forces fail? A deeper understanding arrived with Einstein's general relativity. Einstein didn't view gravity as a force pulling objects. Instead, he proposed that gravity is the result of massive objects warping the fabric of space-time itself. In this model, stars and planets curve the space-time around them, creating a geometry that smaller objects naturally follow, much like a marble rolling on a stretched sheet of fabric. This geometric interpretation elegantly explains planetary orbits, the bending of light around massive stars, and the phenomenon of gravitational lensing. Yet, even this revolutionary model has limits. General relativity is not fully compatible with the quantum nature of the other fundamental forces. This leads to a haunting question: is gravity truly a force, or is it something else entirely? Unlike other forces, gravity cannot be integrated into the standard model of particle physics. The other three forces have carrier particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. The hypothetical particle for gravity, the graviton, has never been observed. This inability of gravity to fit into the quantum framework remains one of the greatest mysteries in all of science. When we consider gravity on a cosmic scale, the puzzle deepens. Gravity dictates the motion of galaxies and pulls matter together into clusters, yet it also plays a critical role when massive stars collapse into black holes. In those regions, gravity is so intense that not even light can escape. These extreme conditions push our current understanding to the limit, suggesting we need a deeper theory that unifies the macro scale of relativity with the micro scale of the quantum realm. Gravity is a theory we feel every day, yet at its most extreme and smallest scales, we do not truly understand it. It governs the entire universe while defying our basic logic. Attempting to build a theory of quantum gravity is the most ambitious challenge in modern physics. In the quantum world, forces are expressed through particles. If gravitons exist, they must be massless, travel at the speed of light, and possess a property known as spin 2. To visualize this, imagine a playing card like an ace. If you rotate it 360 degrees, it looks the same, that is like a spin 1 photon. If you have a king of clubs and rotate it only 180 degrees, it looks the same, that represents a spin 2 particle. An electron, with spin 1/2, would need to be rotated 720 degrees to return to its original state. These strange quantum properties are essential to our hope of quantizing gravity, yet gravity is far weaker than other forces at the subatomic level, making gravitons nearly impossible to detect. Furthermore, general relativity predicts nonsensical infinite values when applied to the singularity of a black hole or the birth of the universe. This suggests the theory is incomplete. Scientists assume that if gravitons exist, they interact so weakly with matter that current technology cannot capture them. Unlike photons, which are easy to detect, a graviton detector might need to be as massive as Jupiter and placed near a dense object like a neutron star just to have a chance. While the detection of gravitational waves in 2015 confirmed the ripples in space-time predicted by Einstein, those were classical waves. Gravitons would be the quantum packets of those waves. This discovery has reignited the debate: are these ripples purely classical, or are they the surface of a deeper quantum process? This brings us to wave-particle duality. Just as light is both a wave and a particle, gravitational waves should have a corresponding particle. However, detecting a single graviton is far beyond us. Some researchers look for indirect evidence, such as graviton-like excitations in quantum materials that mimic the spin-2 behavior in a laboratory setting. While these aren't real gravitons, they offer clues about how gravity might behave under quantum conditions. One of the most radical ideas is that gravity is not a fundamental force at all, but an emergent one. This challenges the traditional view of gravity as an independent power. Theories like entropic gravity and the holographic principle suggest gravity arises from other processes, much like how temperature emerges from the collective movement of molecules. In the entropic gravity model, as objects move, they increase the entropy of the universe, and this increase manifests as the gravitational pull we feel. Another perspective comes from the holographic principle, which suggests that our three-dimensional universe including gravity is a projection of information encoded on a distant two-dimensional surface. In this view, our perception of space-time and gravity might be an illusion, woven together by quantum entanglement at a deeper level. At the same time, physicists are exploring string theory and loop quantum gravity. String theory suggests the basic units of the universe are not points, but tiny vibrating strings. The way these strings vibrate determines if they appear as electrons, photons, or gravitons. It also predicts hidden extra dimensions that influence the structure of reality. Loop quantum gravity, on the other hand, tries to quantize space-time itself, viewing it as a fine fabric woven from discrete loops. This theory suggests that the universe doesn't begin at a single point of infinite density, but might undergo a big bounce, expanding and contracting in cycles. While these theories are mathematically beautiful, experimental proof remains out of reach. Current equipment cannot detect such tiny quantum effects, though scientists are developing new gravitational wave detectors and desktop experiments to look for the pixelation of space-time. Returning to the gravitational waves we have detected, these ripples travel at the speed of light and are created by massive collisions of black holes or neutron stars. These waves allow us to hear violent events in parts of the universe where light cannot reach. Future missions, like the Laser Interferometer Space Antenna or LISA, planned for the 2030s, will be space-based to avoid the noise of Earth's vibrations. This will allow us to observe lower frequency waves, providing data on the early universe and the merging of supermassive black holes. Our current understanding rests on the pillars of quantum mechanics and general relativity, but they clash at the center of black holes or the moment of the Big Bang. To resolve this, Stephen Hawking and James Hartle proposed the no-boundary proposal. This theory suggests the universe has no starting point in time, just as the Earth's surface has no edge. In this model, the Big Bang is a smooth point, like the North Pole, making the question what happened before the Big Bang, as meaningless as asking what is north of the North Pole. Although controversial, it represents a profound attempt to unify the macro and micro worlds within a single framework. That is all for today's journey into the cosmos. I wish you all sweet dreams and a wonderful day ahead. See you next time.